Hello and welcome. We were studying laws of motions, and in this video we are going to learn forces required to keep an object in a circular motion. Now we already know that when an object moves in a circular path, at constant speed v, it is said to be in uniform circular motion. The object or the body having uniform circular motion, has centripetal acceleration. The centripetal acceleration is directed towards the center of the circle. The centripetal acceleration is given by A equals to v square by r, where v is the speed of the object and r is the radius of the circular path. The force that is causing this acceleration is called the centripetal force. The force which is causing this centripetal acceleration is called the centripetal force, and it is given by F equal to mass of the object times v square by r. The direction of both the centripetal force and the centripetal acceleration is always towards the center of the circular path. The direction of both the centripetal force and the centripetal acceleration is always towards the center of the circular path. For example, when a satellite moves in a circular orbit around the Earth, the centripetal force is provided by the Earth's gravitation, which is directed towards the center of the Earth. And when a car moves in a circular path, the centripetal force is the frictional force on tires, which is directed radially inwards. So in this case, the frictional force on the tires are directed radially inwards, and this provides for the centripetal force. Now we'll take an example. You might have seen a stuntman riding a bike in a vertical circular loop. Assuming that the radius of the loop is 3 meters, we wish to find in this example the minimum speed required at the top of the loop for the bike to remain in contact there. So we will find the minimum speed required by the bike for it to remain in contact at the topmost location of the loop. We will draw the free body diagram for the bike, and we will denote the bike by a dot. At the topmost location, the forces acting on the bike are the gravitational force, the normal force, both are acting in the vertically downward direction, and at this point the acceleration of the bike is also in the vertically downward direction, and this acceleration is the centripetal acceleration v square by r. So applying Newton's second law of motion, we find that since both forces are in the negative direction, their net force is minus mg minus Fn, and this is equals to mass times the acceleration. Since the acceleration is also negative, therefore the net force is equal to minus m times v square by r. Now if the bike has least speed needed to remain in contact at the topmost location, then it is on the verge of losing contact. If the bike is having least speed needed to remain in contact, then it is on the verge of losing contact. This means that the normal force is 0. Putting Fn equal to 0 in this equation, we get mg equals to mv square by r, and from this we get v equals to square root of g times r. Now r is 3 meters. So putting the value of r and g, we get v equals to square root of 9.8 times 3, and this comes out to be 5.4 meters per second. So the biker has to keep the speed of the bike minimum 5.4 meter per second at the topmost position so that it doesn't fall. Now we'll take another example. Suppose that we have a circular raised track of radius 200 meters. This track is raised at an angle of theta degrees called the bank angle. This angle is provided so that in the absence of friction, as in the case of wet roads, the car does not slide. Now suppose that we have a car moving on the track at a uniform speed of 20 meters per second. We are required to find the bank angle. We are required to find this angle such that in the absence of friction, this car does not slide. So we are given the radius of the circular path as 200 meters, speed of the car as 20 meters per second, and we are required to find the bank angle such that the car does not slide even in the absence of friction. At any instant of time, the forces acting on the car are the gravitational force in the vertically downward direction, the normal force which is perpendicular to the road surface or track surface, and this car accelerates in the radial direction with the acceleration A equals to v square by r, which is the centripetal acceleration. Now we will draw these forces separately. So we have gravitational force, the normal force, and the acceleration in the radial direction. We will take component of force, normal force in the radial direction and in the vertical direction. So in the vertical direction we have a component of Fn as Fny, and in the radial direction we have component of Fn as Fnr. Now in the radial direction we have only one force and we have acceleration in the radial direction. So applying Newton's second law of motion, we can say that the net force Fnr is equal to mass times A. Now Fnr is Fn sine theta, as this angle is theta, which is equal to the bank angle, and this is equals to mass times v square by r, which is the value of the centripetal acceleration. Similarly, in the vertical direction we have two forces, the gravitational force and the normal component of normal force in the y direction. Now Fny is Fn cos theta, and this will be equal to mg, as there is no acceleration in the y direction. Now we can take the ratio of these two equations. So Fn and Fn gets cancelled. This m and m gets cancelled. We have sine theta by cos theta equals to tan theta, and this will be equal to v square by rg. Now we can put the value of v, r and g and get tan theta as 20 square divided by 200 into 9.8. This gives tan theta as 0.204, and from here we can find theta as 11.5 degrees. So the bank angle, so the required bank angle of the racetrack is 11.5 degrees, such that a car moving at a speed of 20 meters per second does not slide off the road even in the absence of friction.